Hello physics students. In the last video I talked a lot about the concepts of circular motion. I'm going to talk a little bit more about concepts again today, but I also want to talk about and show you how to analyze circular motion with calculations. But first I want to begin by summarizing or reviewing the concepts again. So if something's moving in a circular path, there are three vectors that are associated with this circular path. One is the velocity, which is tangential to the circular path. So notice how when this is spinning around, at this particular instant, this object is moving like this. I put a little vector symbol over the velocity. And the key idea that I really reviewed in a lot of detail in the first video is that there is no outward force, even though you may feel that there is one in circular motion. There is only an inward force acting on objects, which we label F centripetal. It's a vector also. And if there's a force towards the center of a circle, there is also an acceleration. Okay, so I put vector symbols over those. Sometimes on the Regents, this is all they ask about circular motion. Wouldn't that be nice? You draw the three vectors, you get the question right on circular motion. But of course, there's often more to it in terms of the calculations. You might have to calculate the centripetal acceleration. A centripetal is v squared over r. And F centripetal is mv squared over r. So first thing I want to point out is that these formulas are on the reference table. Let me show you. So we're still in the mechanics section back here. So if you look mechanics section and you keep working your way down, you see that the centripetal acceleration formula is right here, v squared over r. But the F centripetal formula they list as ma centripetal. So you basically have to put these two formulas together if need be. In other words, where you see a in this top formula, you put in the v squared over r, giving you m times v squared over r. So there they are on the reference table. Another point I want to emphasize, conceptual in nature, is that also, yes, this thing is accelerating even though this object is not speeding up or slowing down. A lot of people forget that acceleration is also turning. So this object is going at a steady speed, not speeding up, not slowing down, but turning, and it's turning the velocity is always turning towards the center of the circle as it's going around. So that's the acceleration magnitude. Another thing conceptually that I didn't talk too much about in the first video is that you may have to sometimes sketch the path of the object if the centripetal force suddenly ceases to exist. Like in the case of this tennis ball, if I was spinning it and all of a sudden the string broke, and so there's no more force pulling it toward the center circle, and if the object were right here, you have to draw a straight line like this because it's coming around. And I would recommend actually getting a ruler out because sometimes students get sloppy like this or they make a curve to it accidentally. There is no curve because there's no force. Put a ruler down like this. Oops, the ruler moved. And you go like this. Here, you would go as best you can, make it straight up. Not like this, not like this. You want to take your time because you're graded on the quality of the arrow. So you want to really take your time and do that arrow here, here, right? So those are the different kinds of arrows you might have to draw. All right, so those are some of the concepts. Now let's move on to a calculation example using these formulas. So here's the example. Grog the caveman, I picked a name that sounded kind of like a caveman. He spins a 200-gram rock over his head at the end of a 75-centimeter long sling. So maybe he's hunting, and he's hunting like a rabbit. He puts a rock in a sling, like a piece of leather, and he spins this over his head like this, and then he's going to release it to shoot at the rabbit. So that the rock makes 5 revolutions in 1.5 seconds. We're going to determine the speed and then the tension in the sling. Okay, so if you need a moment, I'll create a pause to allow you to copy this down. Okay, so let's move on. The speed, we're going to use the basic formula for speed. Mechanics section, right, back of the reference table, focus. And right at the top, V equals D over T. That's the formula we're going to start with. And so we realize that Grog is spinning this in a circular path. So we need the distance around a circle, which is 2 pi r. Maybe you don't remember that. By the way, that's also in the reference table if you need to on page 5. So if you're, this is the part we usually use, flip to the back of it, you see some geometry and trigonometry for a circle. There it is, C equals 2 pi r. So you don't even have to remember that. You could find almost all the formulas you need on a Regents in this reference table. So that's the distance around, and then we need the time, the distance around once, so we need the time around once. And so what I did is I plugged in 2 pi, and then over here, I had to convert the centimeters to meters. Yes, you always have to do that. So I changed it to 0.75 meters. This is not correct yet because I put 1.5 seconds, which is the time to go around 5 times. But I need the time to match the distance. And there's 2 ways I could fix this. I could either say the distance is 1, 2, well now that's 2. 1, 2, 3, 4, 5. It went around 5 times, so I could go like this and put a 5 up here. Or, if I wanted to, I could say, well, I want the distance once, so the time once, I've got to divide this by 5 to get the time once. If it took 1.5 seconds to go around 5 times, how many seconds to go around once? Divided by 5. One or the other, not both. Both, you're going to get the wrong answer. Let me just pick the 5 and put it in the top. Okay, so we need this again because it's going around 5 times in that 1.5 seconds. Now you punch this on your calculator, and I got 15.7. There's the speed of Grog's rock as he's spinning it around. Now, the tension in the sling, you might say, well, I don't have a formula for tension. It's the F centripetal formula. Any force can go into that formula. So that's what we're going to solve for. Again, on the reference table, we had to use ma centripetal and v squared over r together. This is F, this is A. So we put this v squared over r here and get this. Do it all in one step, why not? So we put in the mass of the rock, 200 grams, and maybe some of you are already thinking, oh, he's trying to trick us again with putting the mass in grams. You're correct. So, well, I'm trying to trick myself. I'm showing you a little pitfall that might happen. You want the mass in kilograms, distance in meters, times in seconds in these calculations. Now we take our speed from the previous part of the problem, and we can't forget to square it, and we're going to divide by the radius of 0.75 meters. Okay, so what you have to do is punch that on the calculator, and I calculated ahead of time 65.8. Hopefully I did it correctly. But there is the tension or the force that Grog must pull on the sling for this rock to be able to go in that circular motion. All right, I'll create a pause, allow you to copy this down. Okay, so before I move on, again, a recap. This is going to happen a lot in this circular motion topic where you have to calculate the speed by doing 2 pi r around a circle over time, okay? And then you might have to fix because there might be multiple revolutions involved, and then just plug into mv squared over r. All right, so now what I want to do is just talk a little bit more about some concepts. All right. So the first thing is that Fc can be any force. It's not its own force, like, well, let me explain. So here's the formula. F centripetal equals mv squared over r. But what we just saw in this problem with Grog is that this can be the tension in a string when you're spinning something around in a string. And that's all tension is. It's just another word for when we're using a string to pull on something. We don't usually say F in physics. We call that a string tension pulling the object. And then it could be also in keeping an object, anything that keeps an object in circular motion. It could be, for example, normal force, like in that infamous gravitron example that I used in the last video. So what's happening is I'm against the wall, and the wall is circular like this, right? So I'm up against it, and then the wall, the room is spinning around, and it's keeping me in circular motion by pushing me towards the center of the circle, right? Outward, a surface pushing outward, that's a normal force. So that case, I plug in the normal force over here. It could be also the force of gravity. Where? Well, think about the Earth around the sun, or the moon around the Earth. So these are for planetary orbits. The force that's keeping the Earth around the sun is that magical pull of gravity through space, pulling the object in. So it could be force of gravity that goes in here. And maybe I'll throw out one more, is that when you're going around a corner in your car, well, you turn the wheel. What allows you to make the turn? We're going to say steering wheel, yeah, but what in the car, what part of the car? And what it is the tires on the road. If the tires fail, like when you hit a patch of ice, you're not going to go around the corner. You need traction. That is the force of friction. Car, around a corner. Oh, I'm getting a little crunched here. Well, hopefully you could read that. Car around a corner. Now, another thing I want to point out is the force of friction. Once again, the formula for that, if you have to ever solve for that in a physics problem, right, this is the mechanics section of the reference table. Oh, a little trouble with focus. And then we go down, down, down. There it is. Force of friction is coefficient times normal force. And so the coefficients are here. For a car, it's mostly going to be rubber tires right here on asphalt or concrete or asphalt rubber tires. That's most likely what it's going to be for a car problem. So just a reminder, force of friction is coefficient times normal force. And remember, we studied this in Newton's laws. If this is a roadway and the car is pulled down with a force of gravity, then what supports the car is the normal force, which is just equal to the force of gravity. So this is the force of gravity. I would go to the front to you with the reference table again, but I don't want to make you too dizzy. But you would look up that formula on the reference table for the normal force or the force of gravity, and it would be mg, the mass of the object times 9.8, or mass of the car times 9.8. So very often in these circular motion problems, you got to calculate this again. It comes up all throughout mechanics. And then when you get that newtons of the tires, you plug it in here. And maybe you solve for how fast you can go around a corner or something like that. So that's another example problem you could do with numbers. The last thing I want to talk about, so this so far is, all stuff that could be on the Regents. Then the next thing I want to talk about is just safety of circular motion and how it can apply to everyday life. It could really be life or death situations. So this is maybe my obligation as a teacher, and now I'm going to go on to my obligation as a moral obligation as a teacher to help you with practical stuff that might maybe keep you alive. Pretty dramatic, right? So here we go. Maybe this is me saving lives. I don't know. We'll see. So safety. So again, F centripetal is mv squared over r. And of course, this is coming from the friction. So what happens when you go around a corner? What are the things? How do these things affect your safety when you're going around a corner? Well, you probably already know from driver's ed. But first of all, mass, in theory, has no effect. Okay, so let's see, how do I want to put that? So mass effect It cancels. I'll put a question mark, and I'll explain why I put a question mark in a moment. But why would it cancel? Remember, you're getting the centripetal force from the friction of your tires. So on this side of the equation, if you put mu mg, notice the mass of the car seems to drop out of the problem. And so the balance of your friction force and the mv squared over r that's required doesn't seem to have mass in it anymore. Now I put a question mark. So in theory, if you're going around a corner, according to just like the most basic kind of thinking, in a car that has no people in it, or you load the car up with 5 football linemen, big, huge guys, and they're packed in the car, and you go around that corner, in theory, it doesn't make a difference. You'll either make the corner or crash, whether the car is empty or with people. But there's more complicated to that because cars can, A, roll over. The other thing that happens is when you have a lot of weight, the car tends to not necessarily fully roll over. So if I crank this way, this side of the car seems to like kind of come up, and now you're more on 2 tires. So there's other effects. I don't want to go ahead and say that for sure mass never matters, because maybe it does actually if we analyzed it with a more complicated situation. But so question mark. But here are some things that we could definitely conclude. And like, for example, the radius effect. Now, what do we mean by the radius effect? The radius effect is how sharp the turn is. And we don't have control over that, right? We come to a corner, the roads, the asphalt's been laid. We got to try and make that corner, or we don't make the corner and we crash. So what's the effect of radius on the force required? We could see that in a graph. Radius, force. And this is like a y equals 1 over x graph, because radius is in the bottom. So if you put 1 over x on your calculator and you just looked at the first quadrant, the graph would look like this. It's this curve that goes down like this and then up like this. A sharper corner, so this is a gradual corner. A sharp corner would be like this, right? And what's the difference? Look at that radius. Look at this radius. So a sharp corner is one with a small radius for the circular path. So this, we could say, sharper turn. Let's suppose here's the original turn, and then we go like this for a sharper turn. Well, at this radius, look at the force, right? But look at this radius, force like this. Now let's go even smaller radius. Oh, look at this force really getting large quite rapidly as you get to here in real sharp corners. So the force required, okay, that increases to infinity. As the radius gets tighter and tighter, the force required to go around that corner, required, goes to infinity, which obviously your tires can't produce infinite force. So if you need almost an infinite force to go around the corner, that's another way to say that you don't have enough force to go around the corner. And that means you're going to go in a straight line path, and you're going to go like this into the guardrails. And you could see this in a lot of places, not a lot, but in some places where you see an off-ramp off like a parkway or something, and then because of the restrictions of the topography, the off-ramp has a real sharp turn. And look at that guardrail. You'll see it all broken up, dented, different colors, paint all. So many people make this mistake. They come in and they don't realize they need so much force. The thing you have to do to compensate is you have to go real slow, make the numerator as small as possible. You have to really slow down to make that corner. Okay, so that's one effect of the radius. The other effect is the effect of the speed. So how fast you're going. How does speed affect how much force you need? Well, if you look at the formula like we've been doing all year, you could see y equals x squared. It's like a parabola. And so what that means, if you were to plot the force required to make it around the circle versus how fast you go, the faster you go, the more the force goes up like a parabola. It's not a linear relationship. It really, the faster you go, it really starts to shoot up how much force you need. Also has implications that lead to a lot of crashes because people don't realize that rapid increase. Let's suppose you increase your speed by 10% going around a corner. So, in other words, you're going, in case one, you're going 30 miles an hour. A 10% increase is 33 miles an hour. People wouldn't necessarily say, oh, that's a huge increase, 30 to 33. What does that do to the centripetal force? Well, an increase of 10% is like multiplying a number by 1.1. 30 times 1.1 gives us 33. But it's a squared effect. So if you square that, 1.1, put on a calculator, see what you get. 1.1 squared gives you 1.21. In other words, that's a 21% increase in how much force you need out of your tires. 30 to 33 miles an hour, you need 20% more force. And maybe that's not a big deal, but if there's a little bit of rain or something like that, that might suddenly be too much. And so you don't make the corner, you crash into the guardrail. How about a 50% increase? That sounds like a lot, but when you think about 30 versus 45 miles an hour, if people see 30 speed limit, a lot of people go 45. They go faster than that, right? But that doesn't sound like you're crazy going 45 when it's 30, right? A lot of people do that. What's a 50% increase? That's like multiplying the original number times 1.5. 30 times 1.5 gives us 45. That's a 50% increase. And when you square that, because of the v squared in the formula, 1.5 squared gives us 2.25. That means the effect on the force that you need is more than double plus. More than doubles, going from 30 to 45 around the same corner, and your tires need more than double the friction to keep you around that corner. People wouldn't realize that, right? Again, that's why guardrails are so smashed up on these off-ramps. And then take something like doubling the speed. A lot of people sometimes go crazy. They're racing, whatever, with their friends, or maybe they're angry that somebody cut them off. So then, they go real fast and they go double the speed from 30 to 60 miles an hour. Plug that in. And you need 4 times as much force to make that corner. All right, so really big effects here and here. The speed and radius really matter on these turns. Slowing down is the only defense, okay? So, all right, if you need a moment to catch up, I'll create a pause to allow you to copy these down. All right, so we did a little with safety and a little with concepts, but today's emphasis was to get you ready to solve numerical calculations on the Regents. Remember, you're plugging in Fc equals mv squared over r, masses in kilograms, any distances in meters, any times in seconds. When you're doing the speed around a circle, it's the circumference over the time for one revolution. So that's another thing that you have to remember. And then you just carefully calculate what you need to. All right, so I hope you enjoyed this video. I'll see you in the next physics video.